In this video, I'm going to very quickly graph two graphs, the cosine function and the secant function. Now, I'm assuming you have already watched my video on graphing sine and cosecant, so I'm going to go a little bit faster this time. First, I need axes. I need the y and x axis. I'm going to go ahead and, on this paper, go all the way to the left, make my y-axis. Halfway through my little graph paper here, I'm going to do the x-axis, or we could think of it as the theta axis. These are the angles that we're putting into the trig functions. And truly the hardest part is graphing the axes, just to start. And it's remembering how, what is actually going in the function. So I'm just going to look at my unit circle to help remind me that we skip 15 degrees, dash, 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 skip 75, and then we're at pi halves. Skip, dash, 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 skip, we're now at pi. Do you see how quickly this is going? Skip, dash, 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 skip, dash is 3 pi halves, skip, dash, 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 skip, dash, I'm up to 2 pi. This represents one full revolution around the unit circle. Of course, it continues in the negative region and beyond 2 pi. I'm going to let 4 squares equal 1 unit on the y-axis. I know 1/2 and 1 are great cosine values, so I'm going to label negative 1/2, negative 1, 1/2, and 1. Now, cosine is pretty on the thirds, so I'm going to for sure label those thirds. If this is your first time graphing, I would highly recommend you graph or you label the entire axis. For this, I'm just going to label the thirds the halves, and then the multiples of pi. And then I can quickly label these points. Cosine of 0 is the value 1. Cosine of pi thirds is 1/2. Cosine of pi halves is 0. Another way to say this, cosine maps 2 pi thirds to negative 1/2. Cosine maps pi to negative 1. Cosine maps 4 pi thirds to negative 1/2. If I input 3 pi halves into the cosine function, it's going to output 0. 5 pi thirds maps to 1/2. 2 pi corresponds with a y value of 1. Now, I am not going to quickly graph lines, like straight lines between these points. This is not a connect to the dot. This is a cosine wave. This is very pretty. So I kind of remember how I used to draw parabolas back in the day. So you start off, or the top is it's almost horizontal in nature. So you start off very slow, and then it continues to fall at an increasing rate. Really, really fast, but then it slows down, and it comes into this point, pi comma negative 1, almost horizontally. That can help you draw a nice curvaceous cosine wave. So it almost leaves horizontal. And when I hit the 2 pi, it kind of comes in from the left, just below and from the left. I have graphed cosine. I have graphed a full period of cosine. Remember, the period is the horizontal distance that it takes this function to repeat itself. And notice I'm at peak to peak. If I were to graph the next pi third, which would be 7 pi thirds, I would start to go back down on my wave, and I would just be repeating myself. So the period for cosine is 2 pi. How about the amplitude of this cosine wave? That is, from a 0 position, how high does this wave go? So you kind of cut the graph in half, and then from that 0 marker, how high does the wave go up? Well, 1 unit. These questions may seem boring at first, but trust me, just wait. All right, let's talk about domain. Well, I can put anything into the cosine function, no problems. All real numbers, or from negative infinity to positive infinity. X-intercepts. Well, I have 2 shown, but I know that this graph just continues in both directions, so I'm going to have an infinite number. So I'm going to use set notation, where I'm going to say it's the set of all x values, such that, or maybe I should use coordinate here instead. That's probably what I should do. Doesn't the sign value, did I just say x? Well, whatever, good enough. Maybe I should do something like this. Nah, I don't know. Different ways to do it. This time I'm going to list the good values. So all of the x values, and remember, I'm going to list a good one. So x is, I'm going to start with pi halves. And then to that, I'm going to add the distance until I get to the next x-intercept. Oh, 3 pi halves. So what's the distance between 1 pi halves and 3 pi halves? Well, this is 1 pi half, 2 pi halves. Oh, so 1 pi. Yeah. And I'm saying pi k, where k is some integer, just meaning every interval of pi to the left and to the right from here on out. Range. Oh, this is stuck between -1 and 1. Sine and cosine are famously bound by -1 and 1. Y-intercepts. Well, sine was at the origin. Sine started at 0, 0, and then kind of went up. Cosine starts high. It starts at 1 and falls down. So the y-intercept for cosine is 0, 1, the ordered pair, the point. Okay, I've listed all that stuff. Now, I'm going to use cosine to help me quickly graph the reciprocal function secant. I'll do that in orange. Secant is the reciprocal of cosine. That is, if I have an output of cosine, I just need to reciprocate it, and I'll have the output for secant. Cosine of 0 is 1, so secant is the reciprocal of 1, also 1. Secant and cosine share the point 0, 1. That's going to happen again at 2 pi, 1, because the reciprocal of 1 is 1. The reciprocal of -1 is -1. Those 3 points are the same. The positive halves will reciprocate up to +2. The -1/2 will reciprocate down to -2. And what happens at these zeros when cosine has intercepts, or when cosine touches the x-axis. Oh, I've done that mistake again. This should be there. At pi halves and 3 pi halves, cosine is 0. 0 reciprocated, I put 0 under a 1. 1 divided by 0 is undefined. So those x-intercepts on cosine become asymptotes for the secant graph. Oh yes, I understand how asymptotes work. I'm going to start with this negative 1 point. To go left in order to touch this point at 2 pi thirds comma negative 2, I'm going to have to decrease. And then that behavior will just continue indefinitely. So again, I kind of come out of here horizontal at first because it's slow, but then it really gets fast. When we are zoomed in this close to the graph, it almost resembles a parabola. But if I were to zoom out just a little bit, and please pause the video, go to desmos.com and graph secant of x, they don't look curvaceous. I mean, there's a curve in there, but they look like a whole bunch of vertical lines because the secant graph has a whole bunch of vertical asymptotes, and the graph is trying to emulate that. From my y-intercept of 0, 1, I'll be increasing, and I'm going to increase really fast, but I am bounded by the asymptote. From 2 pi comma 1, I am going to the left and increasing, but I am bounded by the asymptote at 3 pi halves. So I have graphed in orange secant. So the black graph has nothing to do with the orange graph. The orange graph is the secant function. And you can tell if I were to continue this process, I would just, from here, I would start to increase and I would be repeating myself. So this one, in the negative region, I would come up, I'd have an asymptote, I'd jump down here and I'd have this upside down curve, and I would just keep repeating myself in both directions. I graph secant at the same time that I graph cosine, just for that quick, easy, reciprocal action. I know the values of cosine, the halves and the ones, and those are so easy to reciprocate. If I was asked on like a quiz to graph secant, I myself would first sketch out cosine, and then in a different color, switch over and graph the reciprocal. And then maybe I would go through and like erase the cosine. All right, while I have a graph up here, I could talk about the period. What would be the period of secant? I'll be writing these in orange as opposed to the black. Well, another way to say that, how long does it take me to repeat myself when I start to graph the secant graph? It looks like 2 pi again. So far, all of these graphs have had a period of 2 pi. Amplitude. There is no max value. This is a bad question, but if I do ask it, you could say it's not applicable. It's just not even defined. Like this is just, no, bad question. Domain. Oh, this is going to get tricky. Because all of a sudden I've got some bad numbers. So I can't just say all real numbers. And I can't just give this small interval. The graph goes on forever. So I'm going to have to switch over to set notation to talk about the domain of secant. The set of all of the x values such that x, and I've got bad numbers, so I'm going to list a bad number. X cannot be pi halves. To that, I'm going to add the distance until I have another problem. I have an asymptote at pi halves, and I have an asymptote at 3 pi halves. We said earlier that distance was 1 pi. I'm going to put a pi k on here, where the reader knows that k represents integers. If you need to say that, you can off to the side somewhere say k is an element of the integers, script z. X-intercepts. Does secant have any x-intercepts? And if so, where? No, none. My orange graph never touches the x-axis. Range. I think I can use interval notation here. I can go from -infinity up to -1, included. But then I'm going to have to pick up my pen. So I'm now unioning this with another interval. And I will start this process back at +1. And then I'm good to in positive infinity and beyond. Y-intercepts, same as cosine, 0, 1. That was a very quick run through of graphing cosine and graphing secant. Practice, practice, practice. In the calculus sequence, when we're asked to evaluate some trig value. Half of my students, I can see them, their eyes gloss over, they envision the unit circle, and they get the values that way. Another half of my students, they tilt their head the other direction, and their eyes gloss over, and they instead are picturing the graphs. They've graphed these parent functions so often, they have the shape memorized, and so they know, oh yeah, cosine starts high, so cosine of 0 is 1. And then secant will go up like that. So they have the values memorized that way. You should work on both. All right, we've maybe played with the unit circle enough now. Let's now focus in on these graphs. Graph these things over and over and over and over and over and over and over.